Hey guys, welcome back to another lecture video for Chem 115. In this lecture video, we will learn how to measure the standard cell potential for a galvanic or voltaic cell. So before we go through the calculations, I want to draw your attention to this galvanic cell. So this galvanic cell is composed of two half cells. On the left side, we have a half cell that's composed of a silver electrode that's immersed in silver nitrate solution. And on the right-hand side, we have a half cell in which a copper electrode is immersed in a solution of copper 2 nitrate. And so when the silver electrode and the copper electrode, the metals themselves, are connected through some type of wire, there's going to be a spontaneous transfer of electrons from the metal that is most likely to undergo oxidation to the metal that's most likely to undergo reduction. And so the metal or the electrode that is going to undergo oxidation is known as the anode. And the electrode that's going to undergo reduction is going to be called a cathode. So remember that oxidation means loss of electrons, whereas reduction means gain of electrons. And so one way to memorize the relationships between oxidation and anode, or reduction and cathode, is by creating like some kind of phrase or some kind of name using the letters, using the first few letters of each of these words. So for example, if I highlight the first two letters here, and ox, we can go ahead and say an ox represents anode and oxidation. Whereas here if we use the first three letters, we have red cat. In other words, the cathode is the site where reduction will occur. Okay. And so being in the sciences, it is not enough for us to be able to just identify what metal electrode is undergoing oxidation and what metal electrode is undergoing reduction. What we want to do is we want to be able to quantify the potential between the two half cells. And so this is accomplished through this device called a voltmeter. And so the voltmeter simply measures the potential difference between two half cells and spews it out in as one number. And so the voltmeter simply measures the electromotive force of electrons transferring from one electrode to another. And this electromotive force is simply like a measurement of the difference in potential that gives rise to an electric current. So the unit that we're going to use to describe this potential is going to be volts. And volts simply measures the amount of energy that can be delivered per unit of charge. And so the unit for energy is going to be joules, and the unit for charge is going to be coulombs, or capital C. And so overall, a volt is equal to a joule per coulomb. And so the really interesting thing about this unit volts is that its definition is a ratio of two units. And so typically when you have a ratio of 2 units, this is describing that the unit volt is an example of something that's intensive. So it's describing an intensive property. I'm sorry, not so much describing an intensive property, but it's an example of an intensive property. And so an analogy to this, or something that's more relatable, would be density. And so density is simply a ratio of mass to volume. And so you guys, if you guys can imagine, you have a cup of pure water. And if you take its density, if you take the ratio of its mass over its volume, it's approximately equal to 1.00 grams per milliliter. Now that value is going to change depending on the temperature of the water. So let's just go ahead and scale that image up to involve an ocean of water. And so if you guys were to take out any marine organisms and basically any, like, take away all the salts, and so you just have pure water. So if you have a ocean of water, we can go ahead and take its mass and divide it by volume, and it turns out the density of an ocean of pure water is still going to be approximately equal to 1.00 grams per milliliter, depending on the temperature of that body of water. And so, long story short, what I'm trying to say is that density, much like the unit volts, is an intensive property, meaning that the unit is independent of amount. So you guys can have a cup of water or an ocean of water. The density is still the same. And so you guys can go ahead and apply that with these galvanic cells and voltaic cells. And so if you have like 10 grams of silver and 10 grams of copper, and then you measure its cell potential, and if you were to reduce the mass of the silver and the copper by half, you guys would still get the same cell potential. And we're going to go ahead and use that concept in our calculations a little bit later on. But I thought it would be necessary for me to just bring it up in this slide, since we're talking about the unit of potential, which is volts. Okay. And so, since we are trying to measure the electromotive force of galvanic cells, what we want to do is we want to create a set of standard conditions for scientists to abide by, so that scientists who are performing these electrochemical experiments will be able to obtain values that are comparable amongst each other. And so the standard conditions is going to be 25 degrees Celsius or 298.15 Kelvin. If your cell potential involves any gases, then the pressure, or the partial pressure, under standard conditions is going to be 1 atmosphere. And for the solute concentrations, to measure the cell potential under standard conditions, it's going to be 1 molar. So these are some of the standard conditions that we have to keep in mind. And this word standard condition is simply represented by this E naught. Okay. And so typically, standard cell potentials are rarely larger than a few volts. And so when we go through these calculations, you'll see that sometimes it's less than 1 volt. Sometimes it's a little bit over 1 volt. It's very rare for us to see something that's like automatically like 3 or 4 volts or something like that. And so basically, if you have a battery, if you need to power up your device that requires a higher voltage, then you should arrange your battery in such a way that you get a series of galvanic or voltaic cells. And so by setting it up as a series, you are able to increase the amount of volts that can be extracted, if you will. All right, so when we're looking at two half cells, it's going to give us, so let me take a step back here. So if we take these two half cells, and if they're connected through a voltmeter, this voltmeter is going to describe the overall standard cell potential. So typically when we measure the standard cell potential, we typically will calculate it through standard reduction potentials. And I'll talk more about that in just a second. And so when two half cells are connected, the half cell that has the larger potential, that basically means that that specific half cell is going to acquire electrons and will undergo reduction. Now the half cell that has a lower potential will be the one that donates the electrons and therefore undergo oxidation. And so, in short, the more positive and the higher the value is for your potential, then that means that half cell is more easily reduced. So reduction is typically going to occur for half reactions that have a higher positive cell potential or positive potential. And so looking at this half reaction, here we have fluorine gas at 1 atmosphere, so we're under standard conditions. And so if this fluorine gas were to gain 2 electrons, the potential is going to be 2.87 volts. And so since this value is positive, then that's telling us that reduction is more likely to occur. And so if you guys were to have a half reaction such that oxidation is occurring, so here we have lithium ion, and then we're going to add an electron, so this is a reduction reaction. So here if lithium ion is gaining that electron, and if this value is negative, then that means that this substance is less likely to undergo reduction, and it's more likely to undergo oxidation. And so it is much more favorable for the reverse reaction to occur. So instead of writing out your half reaction in this manner, for you to get a positive potential, you would have to write the reaction in reverse, such that the lithium solid is going to lose an electron, producing a lithium ion. So here in this case, oxidation would produce that positive potential. So overall, when reactions are reversed, the sign of the potential will also be reversed. So that's just something to keep in mind. And so overall, we can go ahead and determine the standard cell potential by taking the difference of the individual potentials of each half cell. And so we can go ahead and use this generic equation to describe that the standard cell potential is equal to the potential of reduction minus the potential of oxidation. And I want you guys to keep in mind that these are potentials describing half reactions. And so we're going to go ahead and take a look at a zinc and copper cell. And so when we're looking at these types of chemical reactions, from here on out, I want you guys to keep in the back of your mind this image of a galvanic cell and or a voltaic cell. The only thing that we're changing is the identity of these electrodes and the identity of these solutions, so that they kind of match up with each other with respect to the chemical equation that we're looking at. And so here we have a zinc copper galvanic cell, and we can go ahead and write an overall chemical reaction such that we have this zinc solid reacting with this copper 2 ion to produce the zinc ion and copper solid, not copper 2 solid, just copper solid. And so overall, using this chemical equation that's written out for us, what we want to do is calculate the standard potential of this cell. And for us to do so, we need to determine which metals oxidized and which metals reduced. And so part of your ability to calculate the standard cell potential is to be able to list out your oxidation numbers. And then from your oxidation numbers, you guys should be able to determine which half is going to undergo reduction and which half is going to undergo oxidation. So let's go ahead and do that right now before I talk about standard reduction potentials. All right, and so oxidation numbers, if you guys recall from the first semester of general chemistry, they are, you guys can imagine them as values that takes a snapshot of the number of electrons each of these chemical species has before the reaction and after the reaction. And so the only thing that's really, the only cool thing about oxidation numbers that's relevant is being able to compare them. So if you guys were to determine the oxidation number of this copper 2 ion, the oxidation is going to be +2, which is great. We are able to identify its oxidation number, but it really has no function on its own. Its strength really just comes from being able to compare oxidation numbers before and after the chemical reaction, so that way we can determine what is going to be oxidized and what's going to be reduced. So I typically abbreviate my oxidation number as ON. So anything that's solid in pure form, its oxidation number is going to be 0. And so if you have an ion on its own, its charge is going to become its oxidation number. So this is +2. And so there is actually a really huge difference in terms of notation. Not sure if you guys are aware of it, but when we're writing the charge, charges are typically written with a number first and then the sign after, so 2+. However, if you guys flip it, and if you guys write it as +2, then you're describing to the reader that this is an oxidation number, not the charge. Even though most of the times they could be the same, they are the same. There are several situations we'll encounter them as we go through this lecture series in which the charge is not the same as the oxidation number. All right, so here in this case, since we have a 2+ charge, that means its oxidation number is +2. Copper this is solid in form, so we're going to assume this is the pure solid. And so therefore it's going to have an oxidation number of 0. So now that we've listed our oxidation numbers, all we're going to do is just compare the oxidation numbers before and after the reaction. And so let me do this one in another color. And so the first thing that you want to do is be able to identify reduction. Reduction is super simple because it's just in its name. So for reduction, you're looking for numbers, the oxidation numbers, going down, right? So when you reduce it, so when reduction occurs, the value itself goes down. And so looking at this, looking what I drew in pink and blue, notice that copper 2 plus goes from +2 to 0. So these numbers in itself is going down, so therefore it's being reduced. So reduction is going to occur for copper 2 plus. And so once you guys are able to identify reduction, then the other side, the other arrow, or the other group, if you will, is known as oxidation. And if you look at the trend for oxidation, oxidation has oxidation numbers that goes up, so it gets higher. So if you guys think about this, oxidation is loss of electrons. And remember, electrons are negative in charge. And so if you lose negative charges, your value becomes more positive. And so with oxidation, you guys kind of have to think about it just a little bit more. But with reduction, it's pretty straightforward. That's why reduction is typically the easiest to find. So reduction is gain of electrons, and since electrons are negative in charge, if you're gaining negative charges or negative values, your value itself becomes lower, right? And so it turns out that the site of oxidation, so it turns out that zinc is undergoing oxidation. So I can write a half reaction for zinc, and I can also write another half reaction for copper. Okay, and so since zinc is undergoing oxidation, and since the charge is +2, then that means it had lost 2 electrons. And so since copper 2 plus is undergoing reduction, reduction means to gain electrons, and since this is going from a +2 to a 0, then that means it's going to have to gain 2 electrons. And so overall, this is going to be our 2 half reactions. And so to determine the standard potential of this cell, what we're going to do is we are going to look at this reference sheet, if you will. And so this is known as the standard reduction potential for many common half reactions. And so the one thing that I do want to highlight and make sure you guys understand is that all of these half reactions are expressed for reduction, meaning that the electrons are on the reactant side of the equation. And so this lists in order a decreasing reduction potential. So we're going from 2.87 all the way down to essentially negative 3.05. And so all of these numbers all of these potentials that's listed in front of you is representing reduction. And so what I'm going to do is I am going to find the value for this copper. So we have 2 electrons reacting with a copper 2 plus. So I'm going to go ahead and use this chart and try to locate my copper that's losing 2 electrons. And so here I have my half reaction that's very similar to what I've written. The only thing is that the electron and the copper 2 ions are just switched on the reactant side, but it's still going to represent the same thing. And so it turns out that the potential, the reduction potential, is 0.34. So I'm going to go ahead and write that the reduction potential is 0.34 volts. And so I'm going to go ahead and look for oxidation involving zinc. And so the tricky thing about this is that since this half reaction is representing oxidation, we actually have to flip this equation so that we can match it up in our standard reduction potential. So we're going to flip this temporarily. So this is zinc 2 plus 2 electrons to produce zinc solid. And so we're going to go ahead and use this equation to temporarily find the reduction potential of this half reaction. And so scanning through my list, it turns out that I have a reduction potential that is negative 0.76 volts. So this is going to be negative 0.76 volts. So right now it's getting a little bit messy. So what I'm going to do is I'm just going to rewrite this in another slide. So here I have copper 2 plus 2 electrons, and that's going to give me copper solid. And the potential, the reduction potential, is going to be 0.34. And so I've identified that the reduction potential for zinc is going to be negative 0.76. Oops. Okay. Now that we've identified the potentials, the reduction potentials for both of our half reactions, what we're going to do is we are going to add them together. Now when we add them together, actually let me take a step back. I'm going to go ahead and show you guys how to solve the standard cell potential in 2 ways. So one, we can go ahead and just take the sum of these 2 half reactions. And if we take the sum of the 2 half reactions, we're going to take the sum of the reduction potentials. Number 2, I'm going to go ahead and show you guys how to use the data that we have currently and plug it into the equation that I mentioned earlier, which is this guy, that the standard cell potential is equal to the potential of reduction minus oxidation. So first, I want to go ahead and show you how to add these two half reactions. So currently, this is reduction and this is reduction, right? We cannot add two reduction reactions together. One of these half reactions must be oxidation, and we already determined that from our work up here using oxidation numbers. And so it turns out that zinc is the one that's, or zinc 2 plus, excuse me. And so it turns out that zinc solid is going to undergo oxidation to produce zinc 2 plus. And so what that means is that I have to take this equation and I'm going to flip it so that it represents oxidation. So here we have zinc solid producing zinc 2 plus 2 electrons. Now when we flip the equation, we have to flip the sign. So therefore the cell potential for oxidation is equal to positive 0.76 volts. And so I'm going to go ahead and just cross out this equation over here. And all we have left is, the only thing that we have left to do is just to take the sum of these two half reactions. And when we take the sum of these two half reactions, reduction and oxidation, we're simply going to cancel out what's in common on both sides of the arrow, which in this case is going to be 2 electrons. And so when we add those two equations, what we get is copper 2 plus aqueous plus zinc solid to produce copper solid plus zinc 2 ion that's aqueous. So what I did is I basically combined what was left over, and what was left over is everything that I've circled. I'm canceling out the substances that are in common on both sides, on either side of the arrow. And so when I add both these two equations, I'm simply just going to add these two values. So overall, the cell potential is going to be 0.76 volts plus 0.34 volts. And if you add them, then you'll just get 1.00 volts. Or I'm sorry, that's not 1.00 volts. Oops, what did I do? So here I have 1.10 volts. And so this would be the standard cell potential for this chemical reaction. Now, if you guys wanted to, apply this specific equation, then what we're going to do is we're simply going to take those All right, so what we're simply going to do is we're going to take these raw standard reduction equations and these standard reduction potentials, and then we're going to just put it inside our equation. And so the standard cell potential is equal to the standard potential for reduction minus the standard potential for oxidation. And so according to our work, we know that it is copper that's undergoing reduction. And so we're going to go ahead and place this number into this equation. So we have 0.34 here, and we're going to carry down the negative. And so according to our work, by looking at the oxidation numbers, notice that it is zinc that's going to undergo oxidation. And so this tells us that this reduction potential for zinc is going to go on the side that is describing the potential for oxidation. And we're going to, when you guys are using this equation, you guys are going to plug in the raw value. So this is going to be negative 0.76 volts. And so this negative actually will flip the sign automatically, much like what we did here manually, where we had a negative value here, but then when we flip the equation, we also flip the sign. And so what we get is 0.34 volts plus 0.76 volts. And if you guys add them together, we'll just get 1.10 volts. So notice that the answer that I get is the same. So you guys have two options of being able to calculate the standard cell potential. You guys can go ahead and just grab the reduction, the standard reduction potentials, and then plug them into this equation. Right? So you guys can grab these standard reduction potentials and then plug them into this equation, but make sure that you guys are plugging them in that would represent the standard potential for reduction and the standard potential for oxidation. Or you guys can manually just do it yourself, where you guys are going to write out your reduction half reactions, and then whichever one is oxidation, you guys are going to flip the equation and flip this so you guys are going to flip the equation, and you guys are going to flip the number, and then you're just going to add them together to get your standard cell potential. Okay. All right. So let's go ahead and work through another example. Here we have this galvanic cell, and it's summarized as copper 2 plus aqueous plus cadmium solid to produce copper solid and cadmium aqueous. And so once again, we need to identify what our oxidation half reaction is and what our reduction half reaction is. And the only way that's possible is if we list out our oxidation numbers. And so since this guy's by itself, we know that it's plus 2. It takes a charge of the oxidation number is the same as the charge for free ions. For metals that are in pure state, the oxidation number is 0. This copper is in its pure state. It's just copper solid. It's not attached to anything else. So there's no like anion, etc., etc. There's no anion or polyatomic ions. And so therefore we can assume that that copper is pure. So last but not least, here we have cadmium with a 2 plus charge. So therefore its oxidation number is plus 2. And so we're going to go ahead and just compare copper to copper before and after the reaction. And we're going to compare cadmium to cadmium before and after the reaction. So what I want to do is I want to look for reduction first, because that's the easiest to identify. What oxidation number was reduced, right, in terms of their value? Well, it looks like the +2 went down to 0. So this is telling us that copper is going to undergo reduction, and that cadmium is going to undergo oxidation. And so if I wanted to, I can just go ahead and just write out my half reactions to represent the reduction and oxidation. So for reduction, I know that I'm going to have copper 2 plus 2 electrons. And it's 2 electrons because here we have a positive 2 charge. And when these two items when these two reactants come together, it's going to form copper solid. So this is reduction. So for oxidation, I have cadmium. So since oxidation is occurring for cadmium solid, that means it's going to lose electrons. And so therefore we have cadmium 2 plus, and when it loses those 2 electrons, I'm sorry, so let me take a step back. When cadmium is undergoing oxidation, it's going to lose 2 electrons, therefore the charge on cadmium is going to be +2. Okay. All right, and so now that I know my half reactions, what I want to do is I want to calculate the standard cell potential. And so if I put both these half reactions together and create some type of voltaic or galvanic cell, and if I allow this voltmeter to determine the standard cell potential for me, what value will I get? And so since we don't have voltmeters and stuff, we're just going to go ahead and use this standard reduction potential. So we're going to use this reference. So in this case, we're still working with copper, so I'm going to leave that highlighted, and its standard reduction potential is 0.34. So I'm going to go ahead and erase zinc because that's not what I'm looking for right now. What I'm looking for is cadmium that has 2 electrons. And so let's see here. So here I have my reduction potential that involves cadmium and the transfer of 2 electrons. And so the standard reduction potential is negative 0.40 volts. So I'm going to go ahead and just summarize both of this. And so since copper is undergoing reduction, it parallels that to the chemical equation that's seen in the standard reduction potential. And so I'm just going to go ahead and say 0.34 volts. So E red is going to be 0.34 volts. Now, since cadmium is undergoing oxidation, this equation, this half reaction that I wrote, is not going to match exactly what we see here because this is describing it as a reduction, not oxidation. So for now, I'm just going to go ahead and keep this number, negative 0.40. So the standard reduction potential is negative 0.40 volts. Now, since this cadmium is undergoing oxidation, then I'm simply going to place these two numbers into my equation, where we have standard reduction minus oxidation. Okay. And so the number that you guys are going to put inside for the potential for reduction is going to be this 0.34 volts because according to this chemical equation, it is copper 2 plus that's undergoing reduction. And so we're going to go ahead and place out 0.34 volts right inside. And so that leaves me with cadmium to undergo oxidation. And so this number here, this negative 0.40 volts, is going to go into this spot in the equation, even though this value is originally a reduction potential value. What will change this value, so what will change this value from reduction to oxidation is this negative or this minus sign in the equation. And so this minus sign will naturally flip your reduction potential so that it represents oxidation. So overall, we have 0.34 volts minus negative 0.40 volts. And so we know that this becomes positive. And so we just have 0.34 plus 0.4. And so when we add both of these together, we get 0.74 volts. And so this is going to be the standard cell potential for this whole entire chemical reaction. Okay. So once you guys get into the swing of things, the calculation is actually pretty simple. You just need to be you guys just need to be able to identify what half reaction is going under oxidation, what half reaction is undergoing reduction. And so just keep in mind that you guys are using reduction potential values. And so you want to be able to identify which half reaction is going to undergo oxidation so that way you guys can properly place the value in the correct location. If you guys don't, if you switch it up, you guys will get a wrong answer. Okay. All right, so I actually want to revisit both of these chemical equations here. So now that I know what's undergoing oxidation, what's undergoing reduction, actually let me do it for this guy. So now that I know which chemical species is undergoing oxidation and which species is undergoing reduction, I want to go ahead and link that up to the idea of anode and cathode in writing cell notations. And so remember that, oxidation is the anode, and reduction is cathode. And so since, and whenever you guys are writing your cell notation, and so Tyler DeWitt covered cell notation in the last part of his video, so hopefully you guys watch that. And so you guys want to place your anode on the left-hand side and your cathode on the right-hand side. So this is going to be side for oxidation, and this side is going to be for reduction. And so for your anode side, which is oxidation, that's going to be cadmium. And so the first thing that you guys are going to write is cadmium solid. And then you guys are going to write the ion. So we can say that this is cadmium 2 plus, aqueous. And then you guys are going to write your double parallel lines to represent the salt bridge. And then when you get to the cathode side, you guys are going to write the first thing that represents reduction, which is copper 2 plus. Let me just move this stuff a little bit over. And then a single line to represent the phase boundary between aqueous to solid. And then last but not least, you guys are going to write the metal in itself. So it's copper solid. So this is the cell notation for the reaction that's shown above. Okay. And so we're going to go ahead and apply that same concept to this copper and zinc. And so for now, I'm just going to go ahead and erase all of this, so that way it's not too busy. So if you guys want to write a cell notation, then we want to make sure that we write our anode, which is the site of oxidation on the left-hand side, and then cathode is going to be found on the right-hand side, so this is going to be reduction. So looking at oxidation, which is this guy right here, the first thing that we see on the reactant side is the solid. So this is going to be zinc solid. Oops. Then we're going to draw a vertical line to represent the phase boundary. The phase boundary is going to represent the transition between solid and aqueous. So the next item that we see on the product side is going to be zinc 2 plus. And so that will effectively communicate to the reader that this is the site of oxidation. And so we're going to draw two parallel lines to represent your salt bridge. And then to the right of the salt bridge, we're just going to go ahead and describe the we're going to describe the chemical species from left to right as we see it. And so since this is the site of reduction, we're going to go ahead and write copper 2 plus first, since that's the first thing that we see. And then we're just going to go ahead and draw another vertical line. And we're going to go ahead and just write in the solid, which is going to be copper. And so your zinc and your copper is going to be your electrode. And so your electrodes is going to be these like metallic rods that you guys see in this picture. And then your ion, your zinc ion and copper ion, it's going to be found inside the solution because it's aqueous in phase. Okay, and so this is how you guys would write the cell notation for this chemical reaction. So when you guys are going over these problems on your own, you want to be able to write a cell notation for these chemical reactions, or be able to go backwards, so go from cell notation to a chemical reaction. And once again, when you guys are calculating your standard cell potential, you guys need to be able to identify which of these two reduction potentials is going to go into reduction and which of these two is going to go into oxidation. And once again, that can be solved by determining your oxidation numbers and comparing them between reactants and products. Okay. All right, so we're going to go ahead and do one more example. So feel free to, if you guys get this concept, feel free to pause this video, work this one out on your own, and then just skip over to the very end for the answer. All right, so to calculate the standard cell potential for the following, we need to identify what's undergoing oxidation, what's undergoing reduction. So here we need to list out our oxidation numbers. So we have a pure substance of gold, so that's oxidation number of 0. The charge of calcium is 2 plus, and so this is going to be plus 2. Gold is 3 plus, so this is plus 3. Calcium, there's no charge, so therefore it's going to be 0. It's a pure solid. And so remember that calculating the standard cell potential is intensive property. And so therefore, I don't really need to pay attention to these coefficients. So you guys don't really want to pay attention to any of your coefficients when you guys are calculating your standard cell potential. Just treat them as you guys have a 1-to-1-to-1 ratio, even though your balanced chemical equation tells you otherwise. All right, so let's go ahead and compare our oxidation numbers. So gold to gold, calcium to calcium. So here we see calcium going from plus 2 to 0. So I've identified my reduction. And so now that I've identified reduction, I need to identify oxidation. So it looks like gold is undergoing oxidation. So what I'm going to do is I'm going to write out my two half reactions. So since oxidation is occurring for gold, that means we're going to lose electrons. So when we're losing electrons, when we write that half reaction, those electrons are going to be found on the product side. So notice that since this is plus 3, that means it has lost 3 electrons. Okay. And so for calcium, this is plus 2 to 0. So here we have calcium 2 plus. And so since this is undergoing reduction, that means it had gained electrons. The number of electrons it gains is equal to its charge for these very simple equations. All right, and so now that I have my half reactions, I'm going to go ahead and look up the standard reduction potentials using my reference sheet. And so for calcium, here its standard reduction potential is going to be negative 2.76. Oops. So this is going to be negative 2.76 volts. And so let's go ahead and look at my, let's go ahead and look at gold. So when you guys are using this chart, be very careful because some of the elements repeats itself, but they're not they're very different. So for example, copper is represented here. Copper is also represented here. Copper is also represented here. So you just have to know which copper that you guys are using. And that's indicative of the number of electrons that's being lost. All right, so for gold, where are you, gold? Okay. Notice that this equation involves the transfer of 3 electrons. And so therefore its standard reduction potential is going to be 1.50 volts. Okay. All right, so I'm going to expedite this calculation by using this equation. So I can determine the standard cell notation by simply taking the difference between the reduction potential minus oxidation. All right, so this is telling me that since calcium is undergoing a reduction, I'm going to take this number, I'm going to place it here. And since gold is undergoing oxidation, I'm going to take this number and I'm going to place it here. And so therefore the standard cell potential is going to be negative 2.76 volts minus 1.50 volts. And so if you guys were to calculate the standard cell potential, I'm going to get negative 2.76 minus 1.50. I'm going to get negative 4.26 volts. And so looking at this answer, this is telling me that my cell potential is non-spontaneous. I think I'm supposed to cover that in the next lecture video, but that just came out, so it is what it is. So what this is telling you is that if you were to create a galvanic cell in which, your gold electrode is going to undergo oxidation and your calcium electrode is going to undergo reduction, then the forward reaction, if you will, oxidation to reduction, transfer of electrons from gold to calcium, is non-spontaneous because its potential, its standard cell potential, is negative. Okay. All right. So I think that's pretty much it for this video. We're going to go ahead and talk about the spontaneity, and I kind of already discussed it here. We're going to look at a couple examples dealing with spontaneity and cell potential.